Okay, so now we're going to get into the fun stuff. The quality control stuff was kind of fun for me because I did that at Pantex. We did the Six Sigma program, and it was kind of scary. We went through 2 weeks of training on how to use statistics to improve our operations. But then at the end, the plant manager who wrote the checks for all of our training, he said, "Guys, this wasn't cheap. We paid $75,000 for each of you to get this training. Now come back to the plant and save us that money. So you got to pay us back in savings." It was really a great experience. And so we would try to keep track of our projects and running tally. And it was kind of a competition between all of us. There was about 30 of us to see who would pay the company back first, and second and so on. And it was really good. I had two really good projects that wiped it out. And I was like, yeah, all right. So, but now we're getting into the forensic chemistry part, the chemistry. And then the last third of the course will be the physical properties. And just as important, but this is the part we've all been waiting for, the chemistry related to crime and punishment, I guess you would say. So here we are at chemical fundamentals, and we're going to start with some review from Chem 2, if I can find my mouth. And so what is this review about? Well, it's about some of the procedures that we do in preparing the samples for analysis. And so this part is just sort of showing how this fits into this organizational scientific committee on drugs. And they've developed these process maps. I showed this on day one. It had this committee. We had committees on every kind of forensic evidence there was, fingerprints, digital photography, and so on. Well, this one is on seized drugs, and they have these process maps. So this is what a process map looks like. And, it has some administrative documentation parts at the beginning, and then it has some like technical assessment where you do the sampling plan. We've talked about the sampling plan, 10% above the first 20 samples and that kind of thing. And then we get into this middle piece, the analysis. So we zoom in on that, and we have things like, is it a plant material? Is it a crystalline powder? Is it chunky? Describe this. Write this into your notes. Is it a fungi like a mushroom or something? Is it a pharmaceutical or an illicit preparation? Maybe it looks like a pharmaceutical pill, but it's got some kind of stamp on it that says it's an MDMA or some kind of illicit drug. Is it a liquid? Is it a THC product? Is it gummy, tarry, waxy? Describing the physical properties. And is it other? Maybe some like gases or dipped cigarettes or something like that. And so that's the characterization of the samples. And then you get into this next part: sample, item description, selection for analysis, preliminary testing, and confirmatory testing. We're going to talk about these separately. So the preliminary testing might be a spot test for a drug. You get a color change. You're like, okay, spot test says it's a cannabinoid. And then you go in for confirmatory testing. Maybe you can crystallize it and get an FTIR. Or maybe you have to go through a liquid chromatography or something like that. So if we zoom in then on this, you see there's also a glossary on these terms, and you have all of these different terms defined. And down here in the sample prep, we see today's lecture, extraction method. Sometimes you need to separate the analyte you want from the matrix and all of those things. So this is where we are in this scheme, in extraction and sample prep method. There's extraction, there's dissolution. Maybe you need to derivatize it. If it's got an acid group on it and you're trying to do GC, it's going to sit on a polar column and come out, a week later. So you want to, this is an exaggeration, but it's going to come out really long retention time, and it's going to be a really broad peak. So the longer something sits on the column, the broader the peak gets, and then it gets hard to analyze it because your integration times are really wide, and you're going to catch other analytes in there, so you're going to have interferences. So we want things to separate, but we also want them to come out quickly. And so if you derivatize it, then you take that acid group and react it with the derivatizer, and then it's no longer acidic and superpolar, and it doesn't sit on the column for very long. And it's for normal chromatography. And we'll talk about that some more. But so that's what derivatization is. And then sometimes you have crystallization techniques. But we're going to focus today on this extraction method down here at the bottom. So this is a part of the sample preparation, the sample cleanup scheme. And it's best if you just have, like, let's say you have some kind of methamphetamine prep solution. I mean, and it's a concentrated solution. It's already liquid. You can just dilute it and shoot it right onto the analysis instrument. That'd be fantastic. That's the best case. It's probably rare, but that would be the best case. Maybe you have a heterogeneous system. You've got a powder on the surface, and you have a well-characterized wipe. So you can wipe that powder up, put that in a test tube, and then later in the lab, you can take that wipe out and dissolve the analyte off the wipe. So there's a heterogeneous way of collecting a sample. If you have powders that may be soluble in acid, base, whatever, then you can use a wipe or a filter to collect your sample and then extract it in a test tube later. Homogenization. So you might have a heterogeneous separation between matrix elements and your analyte, and you want to make it homogeneous. This is what we get with tissue. So if you want to, let's say, test something in blood or even muscle or fat, those are complex matrices. And so you can destroy them with like a little blender, a homogenizer, and destroy all that cellular material, and it releases the analyte. Then you can spin it down in a centrifuge and take the clean supernatant off and then analyze that. That'll be part of your sample prep analysis. They did this, I'm not so familiar with this in terms of human biological tissues, but when I worked at West Texas A&M, it was a big ag school. Kind of like this school is sort of characterized as CJ. We get funding straight from Congress in the state to have like a CJ Center of Excellence here at SAM. West Texas A&M has that same kind of arrangement with the state legislature for agriculture. So we had a lot of agricultural researchers there, and they would take muscle samples of beef cattle and test for hormones and things like that. So they would take the sample, they would stick this little, looked like a little frother that you see if you buy, like if you want to make a frothy latte or something. But this was a little spinny blender, hand blender, that would blend up all that muscular material and release their analytes. And then they could spin it down with a centrifuge, take the supernatant off, and test it for their analytes. Then we have the lab sampling. If you got, again, a big sample, you want to take smaller representative samples. And then this is the key to today's lecture. We're going to use partitioning, chemical partitioning. And you've heard of Le Chatelier's principle. This is the best French I can do, I don't know. But Le Chatelier's principle, and we're going to let it drive the reaction, either all the way to products or all the way, keep it at reactants. So by changing pH, that's what we're going to do. So we're going to let the chemical equilibrium shift to the right and to the left. And so we're going to get into ice tables today. So it'll be a great review. I hope that there are a few people like making faces that are like, this will be the day you get it. Okay? You're a much more mature student now. You're less intimidated by these things. And so we're going to redo the ice tables that you learned in Gen Chem 2. And you're going to say, oh, what was so hard about that? Right? Why did I have trouble with that? Because it's not that bad, okay? And so then we're going to let Le Chatelier's taxi drive us from analyte to, separating the analytes from the matrix or from other interferences, or from one analyte from all the other analytes. And so this Le Chatelier's principle is our taxi that's going to take us either all the way to products or all the way to reactants. So we're going to use this equilibrium to drive our partitioning. So let's review equilibrium and begin at first. So we have the equilibrium constant. It's products on top, reactants on bottom. So if it's greater than 1, that's telling us that products dominate, because all the concentrations in the numerator are much larger than the denominator. So that's much greater than 1. And if it's the opposite, if it's much less than 1, then the reactants are huge and the products are small. So you can just look at the equilibrium constant and know which side of the reaction is predominant. Okay, so we might ask questions. In this reaction, are reactants predominant? Like if you were to test that sample, you would really only detect reactants, or you test that sample and only detect the products. Look at K, and we can use K to drive things forward and backwards, especially if one of those species is an acid or a base. We can use pH to drive this forwards and backwards. So how does this work with us? Well, we're going to use acid base, and solubility to drive this thing forwards or backwards to separate our analytes. So we're partitioning. You know what a partition is, right? The little screen that breaks the room into two or multiple things. So what we're doing is we're trying to get an analyte that we want on one side of the partition and everything else on the other, so that we can identify it. And this is really helpful if you have 2 or 3 analytes and you want to analyze them separately because of interferences. Now, we're using acid and base, and maybe you've seen some of these emails that like warn you against Coke products or any kind of soft drink because it's got acid in it. Okay, and somebody put this on the internet, and it made me laugh because hidden in there, they've modified the ingredients, and it says, of course, phosphoric acid, and then they put poison. So it's not real on the Coke can. Somebody made that up. That's pretty funny. But you get these emails occasionally. Has anybody ever gotten one of these emails? I guess y'all don't get the kind of spam we used to get. It would always be stuff like this, from an aunt or an uncle, and it's like, oh my gosh, don't drink Coke. It's got acid in it, and they try to scare you away from drinking Cokes. And nothing against the brand Coke. I mean, it's sort of in Texas we use Coke to be the general name for all soft drinks, right? Is that like, you ever hear that? Your parents do that? You want a Coke? Yeah, what kind? Sprite. Right? Up in the Northeast, they call it soda. Yeah, pop. Yeah, that's right. I don't want pop. A pop is a orange. Yeah. But anyway, they talk about this, like this one here. You can put a T-bone steak in a bowl of Coke and it'll be gone in 2 days. I don't do that at all. Okay. To clean a toilet, pour Coke in a toilet bowl and let the real thing sit, and it'll clean the stains from the china. Yeah, it may be. But this acid is a very weak acid, phosphoric acid. I mean, it's just there to buffer the pH. Okay. And you know what'll happen to a T-bone steak if you throw up on it? It'll also go away. All right. So look at the pH scale here. We got cola around a pH of 2.8, 3. Look at gastric juices, a pH of 1. So drinking a little bitty phosphoric acid in your Coca-Cola has nothing to, it's not going to touch your stomach. Your stomach is HCl, pH of 1. It's amazing how acidic your stomach is. Yeah, and so if something is soluble in acid and it hits your stomach, it's going to go right into solution, and it's going to go right into your bloodstream. And so that's kind of what we're going to talk a little bit about today, is the physiology of pH. We have all these other things too. Look at saliva and blood. That's around neutral, around 7. And that's also buffered by this phosphate system and carbonic acid too. So we have acids in our bloodstream, specifically carbonic acid, that keeps our pH of our blood stable. Do you know why you get out of breath when you exercise? What's that? Lactic acid, but before that even, you get a carbonic acid buildup. So your muscles use a lot of the sugars, produce CO2, and then that carbonic acid goes up. And so your blood becomes slightly more acidic than normal, and that triggers this breathing, to breathe out that carbon dioxide. When you breathe out the carbon dioxide, the pH comes back up into normal range, and then you stop breathing hard. Yeah. And then over longer term, that builds up lactic acid in your muscles and so on. So, but it's that blood gases, is the CO2 in your bloodstream, which also drops the pH ever so slightly. And your body is just a huge, beautiful pH buffered system. Any slight change to that is going to create a physiological response. Now let's talk about polyprotic acids, like phosphoric acid. Here it is, phosphoric acid. And these are the equilibrium points. So right at the mid-range between that first proton coming off and it being fully acidic, totally protonated, is 7.5 times 10 to the minus 3. Okay, so that's going to give us about just look at the exponent. It's going to be a pH close to 3, maybe a little less than 3. Okay, and here's 8, 6.2 times 10 to the minus 8. So it's almost 10 to the minus 7. So this is going to be between 7 and 8 pH for this proton. So the second proton is buffering something around neutral pH for phosphoric acid. Let's see, what do we have? Here's carbonic acid. Here again, the 4.3 times 10 to the minus 7, also pretty close to neutral pH. So carbonic acid and phosphoric acid in our bloodstream helps keep that bloodstream at neutral. Also, it's in our saliva as well. So let's get into the ice table problems. And here we're calculating the pH of a 2 molar solution of amphetamine, pKa 9.8. And so they're giving us the pKa's, and that's why I brought the Merck index. Back in the day, before the internet, if you needed to look up the pKa for these things, this is just entry after entry of pharmaceutical and drug compounds. And so you would look up amphetamine or whatever. They have all of the, steroids and so on. Crazy names here. Like I can't even pronounce some of these. Okay, we got peanut oil in here too. There's peanut oil. They've got some inorganics too. Here's silver chlorate, all the properties, like its solubility and so on. We'll talk about the Merck index next time too, in terms of coming up with solubilities. Zinc peroxide, zinc phosphate. Here's, let's see if there's anything that you guys can recognize. Doxylamine, dragon's blood. What is that? A resinous secretion found in the fruits of Latin name, and probably other species of Latin name. Habitat, Sumatra, Borneo, India. Interesting. The red sticks, pieces, or cakes, and it tells you about the solubility, and it's used for coloring lacquers and varnishes and coloring plasters. Okay. So anyway, lots of information here in the Merck index. Now there's probably, I know there's internet versions of the Merck index, but you probably have to pay a subscription to get it. Whereas you can probably find one of these at a garage sale for 50 cents. People are trying to get rid of their books and so on. So if you ever see a Merck index, pick one up. It's great reading. You'll doze off in minutes. Okay. So let's get in here to the ice table. So first of all, we got to figure out what amphetamine is. There's some clues here. And one of the biggest clues, do you see anything in the name that would give you an idea of whether it's an acid or a base? Amine. Okay, what is that? Yeah, RNH2, right? And it's got this lone pair of electrons on there. So that means it can be protonated. Okay? And so this is a pKa. So that's the acid dissociation constant, the minus log of it, and that's for the RNH3 plus. The acid form of this has a pKa of 9.8. Okay. So it's 9 point, you have to get above a 9.8 pH to pull that proton off. So this is a base. It's going to hold on to that proton until the pH gets to 9.8, which is pretty basic. Okay? So any pH below 9.8, it's going to grab a proton from water. Okay? And leave behind a hydroxide. And so you're going to end up with a basic solution. So just the very beginning, any of the amines are going to be bases. They're going to be organic bases. Okay? And so we're looking for a 2 molar solution of amphetamine, not the amphetamine acid, but the amphetamine. And so this is our base. We're just going to call this, because these compounds have really big names, we're just going to call that B for base. And this right here is going to be called BH+. Is everybody cool with the terminology? Or we get away from amphetamine or whatever, cocaine or any of these acid bases, codeine, hydrocodone, all of those are bases. And so we've got, oh, what happened? Sorry. The tablet is acting funny in terms of my new laptop. Okay. So let's understand, if we've got the reaction written this way, we've written it as a basic reaction. This base plus water pulls a proton off of water, makes hydroxide. So it's a basic solution, and we want to know about this guy. What's the pH? We put 2 moles of this into solution. What's the concentration of the acid proton and the base protons? So here's a governing reaction for all acid-base chemistry that takes place in water. You've got the equilibrium constant for the autoionization of water, that's Kw, which is 10 to the minus 14. And that's equal to Ka times Kb. So we're given Ka, and we need to solve for Kb. Now, if we take the minus log of these things, we have the pKw, which is 14, is equal to the pKa plus the pKb. So if we take the minus log of 9.8, no, the pKa is 9.8, so we have 9.8 plus pKb. So that's another way to find it. It's very easy. Subtract 9.8 from 14 and we get the pKb. Okay, so let's do the ice table. Let's begin with the most basic thing. Wherever the double arrow is, you've got to put a line here, and that's the divide between reactants and products. Also, in equilibrium chemistry, we don't put water in the table, okay? So we have the base reacting with water. The base is aqueous, and so that's what it's sort of the taking in water into account, and it's producing this acid, protonated base, and hydroxide. So then we have ice, initial change in equilibrium, ICE. And so initially we have 2 moles per liter of the base, and we're going to say we start out with 0 BH plus and 0 hydroxide. And then on the change row, oh, I see I'm calculating Kb first. Okay. So Kb is the one that governs this reaction. And so it's 6.31 times 10 to the minus 5. That's 10 to the minus 14 divided by 10 to the minus 9.8. So this right here is right there. So this is Kb. And that's the equilibrium constant for this reaction, the way it's written. Now, why do they not give Kb? Well, because the Merck and all these things, they just list Kas for all the acid species. So that we're always talking about Ka. But in this particular case, we're interested in a base reaction, so we got to find Kb. Then we do the change row. So if I have some reactant and it goes away, I have a minus X, and then our products are growing, and so those are pluses, plus X and plus X. You see the positive and negative signs change wherever this double arrow is. So when they go past the double arrow, then you have growth of products and reduction of reactants. Everybody cool with this step so far? I haven't done any math, a little bit of math, but the ice table. I just want to make sure that those that were not so happy with this in Gen Chem 2 are happy with it now. And there's no dumb questions. It's your learning. I want you to get it. All right, so now let's get into this assumption. This is what bothered people in freshman chemistry, is I've got 2 molar and I'm subtracting something from it, but then I say nothing happened, right? How can I take X away from 2 and not have anything missing? Look at Kb. 10 to the minus 5. Just forget the 6.3. 10 to the minus 5. That's saying that the denominator is 3, 4, 5. So 10,000 and the numerator is 1. So for every product I produce, I have 10,000 reactants. So it doesn't move forward very much. So my 2 isn't shrinking. Does everybody get that? The 2 is not getting smaller because X is really small. This reaction is only barely going forward. It's a weak base. So it's not grabbing many protons. It's grabbing a measurable amount of protons, but we can measure things down to 10 to the minus, like the best case, 10 to the minus 13. We can measure really small things. So we can measure how much it moves, but it doesn't move much. So I've got 2.00, and I'm subtracting 0.00001, and then I do my significant figures. I round back to the hundredths place, and nothing's missing. That's part of why we did the math on sig figs, is because I'm subtracting something that's way beyond my level of uncertainty. way below the hundredths place. And so then when I round back up, I get back to 2.00. I don't know that anything's missing. So this is the assumption that people struggle with almost always. And so 2 minus x, x is really small, and so it's roughly 2. Super small. Now, why do I keep x on the right, on the products? Because I started out with 0. Okay? Remember when you were a little kid and you had no money, like none, and your parents gave you a nickel? I got a nickel! Right? So you're starting out with 0 products and you get something. So you're happy. You're going to take care of that x. You're going to keep it. Okay? And so any small amount of products produced is going to be significant when compared to 0. Okay, so we keep the x's there, and then we can make up our equilibrium constant, which is, again, BH plus times OH minus. So this is x here, and this is x there. And so that gives us the x squared, divided by B, which we said is roughly 2. Okay, and that's equal to 6.3 times 10 to the minus 5. So we can rearrange this for the OH concentration, which is x. And we're asked for the pH, but we're going to solve for the hydroxide concentration and calculate the POH first. So that's 2 times the acid constant, or the base constant. Take the square root, and we get 1.123 times 10 to the minus 2. If we take the minus log of that, we get 1.948, or 1.949. That's the POH. Okay. And also we can look at this. This is 0.01. Let's see, where's my pen? There it is. Okay. This is really small when compared to 2, right? So if we were to subtract this from 2, we might get 1.99. It's 0.01. So we're right at the edge of what's significant with this assumption. Okay. And so then how do we get to the pH? Well, the pH plus the POH is equal to the pKw. So the pH plus the POH add up to 14. So we could take 14 minus the 1.949 and we get 12.05. So that's the answer to the problem of calculate the pH of this solution. So if we had a 2 molar solution of amphetamine, it would be a 12.05 pH because it's a basic molecule. So it's a high pH, which is a basic solution. Now we could jump right to, like, it's helpful to do the ice table and realize that, we've got x squared over this value here. We could jump right to this line right there if C base over KB is greater than 100. So this is the assumption. So this is the test on that assumption, that this assumption is good if C base over KB. Well, now what's C base? This is the concentration, what we call the nominal concentration. Let's see, find my pen. Okay, this right here is C base. Okay. And this right here is KB. So we've got 2 divided by something times 10 to the minus 5. That's greater than 100. So this assumption would be fine. If you do 2 over 10 to the minus 5, that's greater than 100. You don't even have to use your calculator, right? Because this is 10 to the minus 5 on bottom. Okay, really small number on bottom. So it's greater than 100. So then you could just jump right to that and calculate the concentration of OH minus log on your calculator, and then subtract from 14, and you've got the pH. You can't just get procedural and just do the minus log, and a lot of times people will say, oh, that's the pH, but it's not. Wrong. Because we did this whole thing in terms of base, so that's the POH, and they forget to subtract from 14. So they kind of get muscle memory in doing the calculation, but they're not labeling anything, and they make a mistake, and they calculate the POH and they call it the pH, and they didn't subtract from 14. So it's keep your brain engaged, Don't just do some calculator work and get it wrong. All right, what if that assumption doesn't work? Okay, let's do one of those. Oh, and another calculation that we often talk about is percent ionized. So what percent of this is ionized? Well, remember whenever you're dealing with percentages, we have a part over whole. Okay? And the part is the ionized part. Okay? And the whole is everything. It's the ionized plus the unionized. So it's, it's this x over 2 plus x. Well, x is really small, so it's the x over 2. So this x goes right here. So the ionized piece over the whole times 100%, it's 0.56%. It's not 56%, it's 0.56%. So that's how much of this amphetamine is ionized at 12.05 pH. Okay. Now let's do one where that assumption's not valid. So where C base over Kb is not greater than 100. Okay, so let's calculate the pH of a 0.0025 molar solution of amphetamine. We still have the same Kb. We still have the same ice table, but we've got a very small C base. So we're going to do the change row again. We've got that divide between the minus x's and the plus x's where the products switch to the reactant switch to products. And so then we've got the 0.0025 minus x, and we have to keep the minus x because it's a small concentration. So what do we do in this case? Well, we set up the equilibrium constant just like we know how. We've got K equals BH plus times OH minus. That's x and x. This is x here. This is x there. And this is the 0.025 minus x. So see, this equation is right here. And then we've got to deal with that x. We got x's everywhere. So let's get this in the standard form of a quadratic equation. So we're going to move the 0.0025 minus x over on the left. And I went ahead and switched them, so I have x squared over there on the left. Then I'm going to put everything in the standard form of a quadratic equation where I have ax squared, let's see, ax squared plus bx plus c. You know where this is going, I think. And then we have the quadratic formula, okay? And there's a song associated with it. I never knew, but one time I was doing this lecture and the people started singing a song, and I was like, what are y'all doing? Yeah. So if you could learn the song, that'd be fun. I just never did learn it. Okay. And so let's put everything in there. We've got our B's and our A's and our C's. And so it's not that bad. It's one of those things that's not hard, it's tedious. So you need to learn the difference. Hard is something that's really hard to figure out. This is not hard to figure out. You do a little bit of algebra, and it's just tedious. You got to do the squares. What about this plus or minus thing? Well, go ahead and make your two roots. So you can label one x plus, and that's the positive root. And you can label one x minus, and that's the minus root. So this is a good way to keep track of things. So x minus is when you use the minus sign. X plus is when you use the plus sign. Here's all of your pieces. Minus b, minus b squared, minus 4ac. Okay. And so we end up with these two possibilities for x. And the x is a concentration. So x is a molarity. You see here, x, it's in our ice table. And one of these doesn't make sense. So that's nonsense. It's a negative concentration. So how do we end up with negative moles per liter? It doesn't make sense. Okay. So we pick the positive one. I've never come across a situation with real equilibrium constants and so on where I would have two positive roots. Okay. Now, if you do have two positive roots, one will still be nonsense. and that means that this X here would be bigger than what you started with. And so that's a nonsense one too. So sometimes the largest X is it just can't be. So you'd have to take the smaller X and the one that makes sense. So even if you had two positive roots, one of them would be nonsense because it would be bigger than what you started with, and then the other would be reasonable. But in this case, it's easy. One of those X's turns out to be negative. We can't have a negative concentration, and so we pick the positive one. So now that's the concentration of hydroxide. So we take the minus log of that, and we get the POH, and we subtract from 14, and we get the pH. So look, our pH now is not as basic as it was. It was 12. Now it's 10.56. It's 10.5. Does that make sense? Yeah, we have less base. We have 0.0025 molar instead of 2 molar. You have 2 molar, it's more basic than if you have 0.0025. So this is great. It makes sense. Okay. And we could calculate the percent ionized. We could take the 0.0036. Oh, and we can also see that X is significant, right? If we subtract the 0.000367 from 0.0025, we end up with this. And you see the 0.025 did change. It went down to 0.002133. And then these guys are the 0.000367. So if we take this and we divide by the sum of these two, we got the part over the whole. Actually, let's erase that. If we take that and divide by the sum of both of them, we end up with 0.147 or 14.7% ionized. So it's a smaller amount of base, and so it's a significant amount of the smaller amount of base is going to react with water. And so we've got 14% ionized when it's less concentrated. So that's the worst one. That's the quadratic formula. Okay. And these are much easier than the ones that we're going to have in our body, in the stomach or in the intestine, because those are buffered. And so then the acid or the base column here is no longer zero when we get into buffered solutions. And so then we're never going to have an X squared. We're just going to have a single X. And so it gets easier, way easier from here. So we've already hit the depth of the deep end of the pool, and it wasn't that bad. So a lot of education is psychological. So you may have really struggled in Gen Chem 2. Here we just revisited Gen Chem 2 in one lecture, which took you guys a week or so in Gen Chem 2, and this is the deepest you're going to get in the quadratic formula, and it wasn't that bad. So the psychological part of it is, if you're freaked out about your experience in Gen Chem 2, you're no longer a freshman or whenever you took it. You got to let yourself get it. That self-talk where you're saying, oh, this was so hard, I'll never get it, that's crap, okay? You say, oh, I was never good at that. Just put a comma and put yet. I'm not good at that yet. And so practice a little bit and you're going to get it. Okay. Let yourself get it. So now let's look at the speciation, where we actually drive the system forward or backwards using pH. So the past two problems, we let the system just be in water. We put the amphetamine in water at a high concentration, at a low concentration, and we let the natural equilibrium of amphetamine take place. Now we're going to fiddle with the system. We're going to put it in acid, we're going to put it in base, and we're going to push things forward or backward using the Le Chatelier's principle. Okay? So now we have this calculate the concentration of neutral amphetamine that remains in an acidic solution of pH 2. So now we're dealing with a different reaction. We've got that same starting amount of amphetamine, 0.0025, and we're going to react it in an acidic solution. So now we're adding the base to an acid. So here's our acid. Okay, totally different system, same amount of basic molecule, okay? And I'm wondering how much of that remains, okay? So we're looking at the reactant, okay? And so we've got and again, water, we don't have a column for water. We don't care about that. Here's the double-headed arrow. So this is our division between reactants and products. Okay. And we're putting that in acid. So this is a large amount of acid compared to the amount of base we have. And so let's go ahead and push this reaction all the way to the right and let it come back. Okay, this is a skill that I don't know if you were taught this in Gen Chem 2. I remember a particular Gen Chem 2 problem in the lab that was really hard. It was kind of like this, and it was really hard if you didn't do this trick that I'm about to show you. You had to use the quadratic formula, and it was really kind of an ugly problem. I had a student come and ask me about it, and I was like helping them slowly so that I could think it out, you know. And so this is the best way to do this problem. And I want you to let yourself get this. So here's the change, right? And what we're going to do is we're going to push it all the way to 100%. So we're going to push this all the way to the products and see how much comes back. Okay, so this is our new initial conditions. So look, we don't have just an ice table. We have ice, we have an initial, we have 100% change, and a new initial. So how do we get to 100% change? We take the limiting reactant down to 0. Okay, so what have we done? We've taken this point 0.0025 and we've gone to 0. So that means X is 0.0025. Okay, and so that means when I have 0.01 minus 0.0025, I end up with 0.0075. Does everybody get that? That's easy to do, right? And then here I've got 0 plus X. Well, X is right here, 0.0025, and so that's what I have over here for BH plus. Now I've got a new initial. I'm all the way to the products, and I'm going to see how much comes back. Okay. So now look at my X's that switched signs because I'm going backwards now. This is now my reactant. It's going to produce a little bit of acid and a little bit of base. It's going to go backwards because nature hates zeros. And I got a big fat 0 right here in this column. So it's going to come backwards just a little bit. Okay? And this helps me avoid the quadratic formula. I don't have to do the quadratic formula because I'm only going to have one X. Okay? So let the reaction run backwards. That's going to be X, 0.0025 minus a teensy little X. And I'm going to end up with 0.0025. Nothing's going to change. X is going to be super small. At 0.0075 plus a super small x is 0.0075. And then I got 0. Remember the kid with no money? He's going to be happy to get one little tiny minuscule amount of x. And so we're going to keep that x there. Okay. So then we write out our equilibrium constant. We got B times H3O plus divided by BH plus is equal to Ka, and that's going to be 10 to the minus 9.8. So you see we have one X here. We've got the H3O plus on top, which is the 0.0075, and the BH plus on bottom, the 0.0025, and then we've got the equilibrium constant there. So we can solve for this X, and it's 10 to the minus 11, really small. So our percent ionized is 0.0025 divided by the sum of 0.0025 plus the 10 to the minus 11. And so it's essentially 1. It is 1. It's 100% ionized. Remember when we didn't have the acid in this reaction, the B was only, it was the previous problem, it was only 14% ionized. We added acid in there and we protonated every one of the B's. Okay. For us to have an unprotonated B in this situation, we'd have one unprotonated B for every 10 to the 11 protonated B's. Think of how many you'd have to have. You have to have 10 to the 11 or 10 to the 12 molecules of BH plus before you have a single B without an H plus. That's kind of what the equilibrium constant's telling you. Okay, so it's pretty impressive. And then we could take that, that's the concentration of B. We could look on here, okay, what's the pH of this situation? Well, the pH really, it's this minus log of the hydronium ion concentration, so we could take that, and it would be something times 10 to the minus 3. You're looking here at what the natural log, the log of this concentration is telling you where the numbers begin. So if I've got 0.001, 1 1/3 decimal place, if I take the minus log of that, it's 10 to the minus 3, so the pH is 3. Okay. If I had 5 zeros, it'd be 10 to the minus 5. So you can kind of look at these concentrations, and if you're familiar with base 10 logs, it's telling you what decimal place the acid concentration is. Any questions on this one? We're going to do another one. Yes?
That 0.01 molar, is that just arbitrary number chosen?
Mm-hmm.
Okay.
Mm-hmm. Yeah, and it's not a very strong acid either. It's a 10 to the minus 2, so it'd be a pH of 2. So how did I do that? Well, look at 0.01, right? 0.01 is 10 to the minus 2. If I take the minus log of that, the log brings that exponent down. Now it's negative 2. If I take the minus of that, I get a positive 2. So we're looking at 0.01, that's a pH of 2. 0.001 is a pH of 3. 0.0001, that's in the 4th decimal place, that's a pH of 4. So it's real easy to use the ones. If I tell you, what is the acid concentration at a pH of 6? Well, it's 0.00001. So 5 zeros and a 1. That's pH 6. Okay. So this is great. You can do logs in your head, at least base 10. It's just what decimal place you're in. And did anybody not know? I mean, it took me a while to kind of like clue into that. pH minus log was a mystery to me for at least until I was a professor. And then I was starting to think, I was doing problems so much on the board. I was like, hey, it's not so bad. I could do this in my head, kind of, you know. And it was always a trick teaching Gen Chem 2. We'd have something like 4.5 times 10 to the minus 5, and I'm sitting here looking at it. I was like, well, I know it's going to be around a pH of 5, but it's a 5 times 10 to the minus 5, so it's getting a little closer to a pH of 4 because it's bigger, not less. And I would try to come up with the log in my head at the board while the students are over there, and I try to beat them. They're doing the calculator, and I'm trying to do it in my head. So if you can do that, you do that in the workplace, people are going to be like, whoa. Then you're going to get called Nash again, and they're going to laugh. So it's a good laughter. Okay. Now, how does this figure into the body? Well, this tells us where these drugs will be absorbed primarily. So the pH of the stomach is 1 to 3. Okay. So the acid pumps in your stomach are pumping out that acid to tear up your food and break down the compounds and so on. And so if it's acid soluble, like a base is, when you protonate that base, all of a sudden it's charged and it's water soluble. This amphetamine's a big old organic molecule, not necessarily happy in water when it's neutral. You put a proton on it, now it's charged, and water can stabilize that compound in water, and it'll go into the bloodstream. So if you take a base by mouth, it hits the stomach, it's protonated, and whoop, it goes right into the bloodstream right away. So that's the rapid release. If you want a rapid release pharmaceutical, you want it to be an organic base because it's protonated in the stomach, and as soon as it hits your stomach, it's going to go into your bloodstream. And if it's like a headache medicine, that's what you want. For a good headache medicine, you really want an organic base because it's going to go into the body right away. If you want an extended release something, you probably want an acid because it's not going to be soluble in the stomach. It's going to take a lot longer to go into the body when it gets into the intestines because the intestines are pH 5 to 7 in the intestine. And again, it's a long route. It starts out at 5 and ends up at 7. So somewhere along the intestines is going to be the sweet spot for absorption of that molecule. And then you get into the colon, pH 7 and 8. And then you start getting, your acids are going to be soluble in a basic situation because they're going to be deprotonated. So as soon as the proton comes off the acid, you have an acid minus, an anion, and now that's water soluble. So if you deprotonate an acid, it's water soluble, it goes into the blood. If you protonate a base, it's water soluble, it goes into the blood. So we always have this partition in our body. So that's a tiny bit of pharmacology. We can use the same thing in the lab. If we have a organic phase and an inorganic phase, that's what the next lecture is about, how to drive things into the organic phase or into the inorganic phase. In our bodies, we have fatty tissues and we have the bloodstream. And the bloodstream's aqueous and the fatty tissues are organic. And so you can drive things into the organic phase or keep them into the aqueous phase. And our body's controlling all of that. And I swear that's what's happening to me at 3 a.m. when I drink a lot of caffeine. I don't know this for a fact, but I can drink coffee all day and go right to sleep, 10 o'clock, 11 o'clock, whatever, and not have any problems. But something happens physiologically when that caffeine is released at 3 in the morning out of my fatty tissues, and I'm bing! I'm like, wow, I'm not just awake, my heart's racing, and I'm ready to go. And I don't want to be, I want to sleep. So, that's just getting old, so it's too bad. I love coffee. So bases, that's just basically what I said. Bases are protonated and more soluble in the stomach. Acids are deprotonated and more soluble in the intestines. Okay. And I didn't realize this. I have a doctor friend at church, and so we talk about this stuff all the time. And I said something about why people get dehydrated when they have diarrhea. You can get dehydrated like that if you have an upset stomach and you have to take the Pedialyte and all of that. And he said, well, the colon is kind of like the camel's hump. So why does a camel have a hump? They store water in there. So when they go long periods without water, water starts to dehydrate out of that hump and keep the body hydrated. Our colon is our hump. And so the food that's stuck in the colon will absorb or desorb water to keep our body hydrated. And so that's interesting. So that's the trick too, why you want to constantly drink water, so you keep that colon hydrated and stuff moves through. If you get really dehydrated, stuff doesn't move. I know we're talking about nasty stuff, but that's what's happening in your colon, is it's your water reservoir. And so that's interesting. So if you have diarrhea and it's completely emptied out, you have no reservoir. And so you can become dehydrated right away because it doesn't have the matter in the colon to suck the water out and keep the body hydrated. I thought that was really interesting. So find a doctor friend, and they're fascinating to talk to. Okay, so let's talk about drug absorption. And here's a particular drug, dimetrazine tartrate. And it's really not relevant what kind of drug it is, but what you need to know is that it is a base. Okay? And tartrate, you see this ATE. Okay, that's an anion. And so in the name, you see it's paired with an anion. And so that means that it's a base. It's been a protonated base. So the proton of the tartrate is stuck on the base, and so that makes it water soluble. So this is a water soluble formulation of this phendimetrazine, and so if you were to ingest this drug, it's already protonated. It will go right into the bloodstream in the body. Okay. A lot of times you'll see HCl, so you might see phendimetrazine HCl, and whenever you see that in the name, again, it's paired with an acid. The proton is on the base, and the Cl is the counterion, the chloride, and then that's a salt, and then you could ingest that and go right into the body. So we'll do that. Ice table, we want to know how much is absorbed in the stomach. So the stomach has a pH of 1, and so that's going to be right here in the acid column. We've got the double-headed arrow here, so we're separating our reactants and products at that double-headed arrow. This is a buffered situation because it's the stomach. So this 0.1 acid concentration is going to be 0.1 all the way down the table. So we do our pluses and minuses for the X. And we have BH plus. We've got 1, mole per liter, I guess, if you want, in the BH plus, minus X. Again, it's unchanged. And so we've got this equilibrium constant here. And it's going to be the B times the H3O divided by BH plus. Again, this is an easy problem because we just have the 1x here, okay, for the B right here. Okay, we're given the pKa at 7.6. We can solve for x. So 2.5 times 10 to the minus 7. Every time you calculate an x, so this is x, and so you can come up here and you can sort of check, like if this approximation bothers you, which it did when I was young. Whenever I was doing ice tables, I would say, how do I know? I mean, I say x is insignificant, but how do I know? Well, you just solve for x, so then you can check your work. So you can assume it's insignificant, solve for it, and see if it's a valid assumption. And yeah, 1 minus something times 10 to the minus 7 is roughly 1. So you can see that that was a safe assumption. We're not really subtracting anything that we could detect. Okay. And so that's the concentration of the base. What about and we could calculate the percent ionized, and it's 100% ionized in the stomach. What about in the colon, a pH of 7.6? So now the pH is 7.6. How do we calculate the hydronium ion concentration? It's if H3O plus, the pH is the minus log of this, equals, oh, I don't have enough room, just a second. So that's the definition of pH. Okay, how do I get to the concentration? Let's do the algebra here just so I can show it to you. Let's move this minus sign to the other side. So I have the minus pH. And then how do I get rid of the log? I take the antilog. And so then the antilog is 10 to the minus pH is equal to H3O plus. So that's what I've done here. This 10 to the minus pH gives me the hydronium ion concentration. So 10 to the minus 7.6 is 2.5 times 10 to the minus 8. That's the pH in the colon. That's the concentration of acid in the colon. Really, really small amount. I do the x's. Again, because it's buffered, even though that's a small number, let's say my colon gets a little more acidic, the body absorbs that acid and keeps it at 7.6. If I have a little less acid, the body responds and keeps it at 11.6 or at 7.6. So these physiological systems are buffered, and we can do the same thing in the lab. We can like put in a certain amount of acid, take a certain amount out by putting base in. We can buffer things too. So even though it's a small number, 2.5 times 10 to the minus 8, we're going to keep that 2.5 times 10 to the minus 8. We have 1 minus x. We're going to keep that minus x and see what we get. So we have this equation. This one actually doesn't need the quadratic formula because we don't have a x squared. And so then what we do is we move this x over to the other side. I take 10 to the minus 7.6, which is 2.5 times 10 to the minus 8. And then we move this other x over, and we end up with 1 equals 2x, and x is equal to 0.5. So this goes in here, there, and there. And we end up with half of our base is protonated, and the other half is not protonated in the colon. In the stomach, our base is 100% protonated. In the colon, it's 50-50. Now you may say, well, that doesn't really favor absorption into the bloodstream because only half of it is protonated. But when it has access to the bloodstream, it kind of flows into the bloodstream. It's kind of like osmotic pressure, but it flows into the bloodstream and is diluted is distributed across the whole body, and then the other half starts to split, and so it'll go into the bloodstream slowly, or it'll come out of the bloodstream. Let's say the bloodstream is concentrated, and it'll go into the colon and establish this equilibrium with the colon. Any questions on these two? Take-home lesson on this is is in the stomach. This essentially the X is insignificant in the colon. Again, it's unchanged, so you see that it's buffered, and therefore the X is insignificant. So it's whenever it's buffered, it's unchanged. So we can just pick that pH for the colon. We can pick that pH for the stomach. So we could calculate, we could take all of this algebraically, and if we do these problems over and over again, we don't necessarily have to do the ice table. Now, I like want to raise a red flag and say, be careful, because if you don't know what you're doing, cutting to these shortcuts, again, if you don't engage your brain, you'll get an answer on your calculator, but if you don't know what you calculated, you're going to get things wrong. So you need to know when to use these shortcuts. It's so dangerous that some of the professors here really criticize me. They don't criticize me directly, but they say, these people teach the shortcuts and then the students make mistakes. And I'm like, well, that's true. So they don't teach the shortcuts. I teach the shortcuts because I want you to engage your brain and not waste your time making up a bunch of tables, right? If you want to calculate the percent ionization, you could use this. You do the algebra once, and then you can use the shortcut. So here's the algebra. Percent ionization is part over whole. Okay, so this is for an acid. This is the ionized acid. That's the ionized part. Over the whole, which is everything. That both the deprotonated and the protonated acid. So that's everything, and then the ionized part's on top. So that's what we mean by percent ionized for an acid. Okay. So let's flip this upside down, because I want to be able to get to this HA and the A minus individually. So I'm going to flip the whole thing upside down. Okay. Now I see that the A minus over A minus is 1. I can take that denominator and split it, so I have the sum of two fractions. So the A minus over A minus becomes this 1 right there. And then I have the HA over A minus right here. Everybody cool with that algebraic step? Okay. And now I'm going to move that 1 over to the other side, over here. And so I have HA over A minus is equal to 1 over percent ionization minus 1. So we've done that. Just sort of put that in your pocket. Let's now go over here to the equilibrium constant. So I've got the equilibrium constant written out. I could take the minus log of everything. Okay, so the minus log of the hydronium ion concentration, this piece right here, is the pH. And then I have the minus log of A minus over HA. And if I wanted to flip that to a plus, I could flip the fraction. So if I flip this fraction, I make this a plus. And so that right there is the Henderson-Hasselbalch equation. So how many people remember that name at least? Yeah, good, okay. It's kind of a shame. I don't know who Henderson and Hasselbalch are, but they did 2 steps of algebra and they got their name on an equation. What the heck? Wouldn't that be nice? It must have been a long time ago when science wasn't doing very much, right? That's pretty easy. So let's take this A minus over HA, okay? And we're going to take this one up here, this flipped one, and we're going to say minus log. So if I take the minus log again, we would flip these again. And then we have HA on top over A minus, and we could take this piece and stick it in here. So we're going to take that piece out of our pocket and put it in here. Okay? Now let's isolate that log. Let's take it to the other side, and let's take pH to the other side, and we end up with this equation. Log of this piece equals pKa minus pH. Let's get rid of that log with the antilog. So we have 10 to this. We'll get rid of the log. So we have this, okay? And now let's move the 1 over to the other side. So we have a plus 1 here. And then we're going to flip it upside down. And we end up with this. So this is my equation for buffered percent ionization. We did the algebra, and we have this. So if we know the pKa and we know the pH, we can calculate the percent ionization. No ice table needed. That's nice, because a lot of times in a problem, I'm given the pH of the stomach, pH of the colon. I know the pKa. I can calculate how much is ionized. Okay, and so I did a whole bunch more algebra than Henderson-Hasselbalch. So I want to call that the Williams equation. Yeah. So you got it here. Spread the word. I don't know if I should say this on the video, but let me cover it up. The first and second editions of the book didn't have this equation in it. And yet I started showing my videos online. The third edition of the book shows this equation. They don't do the derivation though. And I was like, did they watch my videos? I wonder. So I can't say that they did or didn't, but anyway, it's pretty fun. Now, yeah, exactly. I'm sitting here thinking, those people. No, it's great. It's just algebra. I don't deserve an equation for it. So this is the percent ionization for the acid. Now notice you have two variables. You have pKa and you have pH. So let's plot it out. So this is pH here and this is pKa here. So when the pH is greater than the pKa, we've deprotonated the acid and we have A minuses, right? So what does high pHs mean? High pHs mean base, right? So I've ripped the proton off the acid and I have an anion. And anions are soluble, so that's going to be aqueous, okay? And so this, what happens when the pKa equals the pH? Well, that's halfway to equilibrium. I don't know if you remember the titration curves, but it kind of looks like this. If I've got an acid with a pKa of say 2.2, you know, when I have a really low pH and I'm sort of titrating with strong base, it's mostly the acid, but then eventually I get halfway to equilibrium and I have a pH equals to pKa. I'm halfway to equilibrium point. When I go past that, I've deprotonated all the acid and I get a color change and my titration is over and so on. And so we've seen these titration curves, and this is just every titration curve you could have for every acid you could have. So we were up here at 9.8 for amphetamine, and so we would get them over here and we would have to get to a pH of, what was the first one? It was 12 or like 10.5 were those pHs for those two equilibrium situations. Okay. Now this is the percent ionization for an acid. If you're calculating it for a base, you can use the pKa and the pH, but it's flipped, okay? So let me skip ahead. So you just use that equation, which will be on your little exam equation sheet, but if you're calculating it for a base, it's 1 minus the percent ionization for an acid. So the base is ionized with the BH plus. So notice how it's reversed from the acid. When you're at high pH, the base is deprotonated and it's not ionized. And what we're calculating is percent ionized. So the acid, it's ionized at high pH. For the bases, it's ionized at low pH. Okay, so you can calculate it with the pKa for that amphetamine. We could put in the pH and the pKa, and then we could calculate the percent ionization for the acid, and then we take 1 minus that, and we get the percent ionization for a base. So if your molecule is a base, this is the equation you use. If your molecule is an acid, you do not have to do the 1 minus thing. So this is where the thinking comes in. You can have that equation and you can calculate it, but if you forget which one you're calculating, then you're going to get the wrong answer. So you got to engage the brain. You can't just do the calculator. Okay. Why do we care? We're caring about what's water soluble. Both for the body, what's going into the bloodstream, that's the pharmacology piece, and then for partitioning in the lab, we're going to have an organic phase and an aqueous phase. And we want to know if it's unprotonated, it'll be in the organic phase, because these are all organic molecules, or I should say unionized. If it's unionized, it will be in the organic phase. If it's ionized, it'll be in the aqueous phase. And we have two different types of ionization. We have anions for acids. We pull a proton away, it's an anion. And we have the cations for the bases. You protonate a base, it's a cation. So that's why we don't say, we say ionized, not protonated, deprotonated, because protonated acids are neutral, protonated bases are ions, and just vice versa, right? Deprotonated bases are neutral, and protonated bases are ionized. So we're trying to determine where is this thing ionized, because that's when it'll be in the aqueous layer, and then when it's not ionized, it'll be in the organic layer. So now we're sort of set up for the next lecture when we get to liquid-liquid extraction, because we'll have an organic layer and an aqueous layer. And y'all did that in organic, right? Y'all did the SEP funnel, vent, 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 and we do that in the forensic lab too. It's kind of an old school method, but it's still something that's useful. If you understand liquid-liquid extraction with real liquids, then you'll understand partition with columns and things like that. So they may still have some like real sort of packaged columns where you could do the extraction, and it saves time. But if you understand liquid-liquid extraction with the old school methods, you'll understand the modern things that you run into. And so this is sort of this idea, the summary. You have acidic compounds and where they're soluble. So they're soluble in basic solutions. Basic compounds are soluble in acidic solutions. And then you get amino acids and things that have a basic group and an acid group on the same molecule, and that's nutty. Okay, so here we have, it's really soluble in the basic, it's really soluble in acidic, but right in between, it's kind of less soluble, and it might go into the organic phase if you're in between the two, the pKa and the pKb. And so that's what we have for amphoteric molecules. We've gone a little bit over, but that's good. Good questions, and we'll see you next time.